So it's about the relation between species mixture, the design of those mixtures, and the weed suppressive ability. So I like to talk about weeds in agriculture first. So what traits do make that certain plant species can develop as weeds in an edible setting? The reason partly is also that if you know your enemy, you're probably better able to combat them. Then we'll look at how increased crop diversity relates to weed suppression. Is it an effective component of an integrated weed management strategy? So does it really matter? And which mechanisms are operative if it works? And then from there on, I would like to look at the design of the intercrop and see how that affects the weed suppressive ability. Look at various design factors like species composition, the mixing ratio of species, the total plant density, and then finally also look at mixtures where the species have a less intimate mixing, like the strip cropping system. So that's more or less the content. So if you look at weeds in agriculture, farmer will be preparing his field. He might be plowing, might be conducting a seedbed preparation, and then sow. And after that, you'll find the crop establishes, it emerges. But next to the crop, we also find a kind of spontaneous vegetation. And if those are serious weeds, then for sure we have to do something against it, because otherwise a fierce competition between the two will occur, and that will have its negative drawback on the yield of the crop. Now, which species develop as weeds in agriculture? And then we can look at the agricultural field, and it has two important characteristics. Usually there's a high level of disturbance, so all kinds of activities are taken and that will disturb the field. At the same time, usually there's also a low level of stress, means that plants do not really suffer. And that then corresponds with a classification that was made by the plant ecologist Grime, and he indicated that if you characterize the environment, you can use two characteristics for that. One is the level of stress, which might be low or high, and another one is the level of disturbance, which also might be low or high. Now, if you have a low disturbance and a low level of stress, then in the end, the more competitive species, the species that are better able to capture the resources, they will become dominant. If you have a high level of stress and a low level of disturbance, usually those species that are well able to deal with those stress factors, for instance, if the salt level is high, then those species, so the stress tolerators, they will dominate. If you have an environment with a low level of stress and a high level of disturbance, like an edible field, then you usually have ruderal species that start to dominate. So ruderal species and weed species, they usually go together. And this is the classification that Grime made, his triangle. And on those axes, you find competition, you find level of disturbance, and you find level of stress. These, of course, are the extremes, so the stress tolerators, the competitors, and the ruderal species. But of course, you can also find environments that more or less fit in between. Characteristics that make ruderal species successful or that define ruderal species, usually a very high initial growth rate. Whenever a field comes available and vegetation is cleared, they have to rapidly colonize that area. So usually they have a very high initial growth rate. Apart from that, they also have a short vegetative period, so they relatively early start to produce seeds because that's how they survive. They also produce a high quantity of seeds, relatively small seeds, also to give them better chances as a population to survive. And most those species, the seeds of those species also contain a certain level of dormancy, so that if conditions become favorable, not all of the seeds will germinate at the same time. Some are dormant and they will stay. So if unfavorable conditions happen after germination, there still are plenty of seeds present in the soil. So this typically is what characterizes the ruderal species. Very important is that they have a very high initial growth rate. So they settle relatively fast if you end up with an open space. Well, if we don't control them, then usually there will be a huge yield loss. And the relation between wheat plant density and yield loss is nicely described by Cousin's equation. This is how the equation looks like. And what you can see from here, if that wheat density is low, the implication, the impact of those weeds is usually relatively high. When wheat density increases, also the level of yield loss increases, but gradually at a lower pace, because next to the competition with the crop, the weeds, of course, also start to compete among each other. So the yield reduction, on the one hand, determined by the wheat density, on the other hand, by the competitive relation between the crop and the wheat, and that is characterized with this initial angle. So if you have a highly competitive wheat, the angle is relatively high, and you'll end up with a high maximum yield loss. But if you are dealing with a wheat that is not that competitive, the angle will be lower, and it might also be that the maximum yield loss you obtain at extremely high wheat plant densities is not that high. So two aspects related to how weeds influence crop yield. Then how can we deal with those weeds? Well, one way is curative control. That might be by various means, herbicides, mechanical weeding, hand weeding, all of them contribute. But the principle, of course, is all the same. What you try to establish is a reduction in wheat plant density, and as a consequence, the yield loss will reduce. Then we can also think of another way, because it's very important to combat the weeds. The weeds are characterized by a high initial growth rate, and that means if you have a crop with a relatively fast canopy closure, then you're able, well, to compete relatively well with those weeds. And there are various measures through which we can increase the competitiveness of the crop. For instance, transplanting, meaning that the crop plant doesn't have to start from a seed, but is already distalled. That gives a clear advantage in terms of competitive ability. You can increase the seeding rate. You can go for more competitive cultivars. You can also improve the positioning of the crops. The more uniform the plants are positioned, the more rapidly they will cover the soil. So also that has a positive effect on the competition of the crop. And if you go back to Cousin's equation, in fact, what we are doing, if we take those measures, we manipulate the slope of this curve, we manipulate the maximum yield loss. And so this is another way of dealing with weeds. And if we now think about intercrops, then the question is, okay, if instead of a monoculture, we use an intercrop, does that result in a faster canopy closure? And that is what was investigated, for instance, by Daniel Baumann from Switzerland, from Wädenswil. He conducted a PhD thesis with us, and he focused on a system, leek and celery. And leek, in this case, is the problem crop because it grows relatively slow initially. It leaves open a lot of space. It's not very leafy. And the celery is something very different, a very leafy and relatively fast growing crop. So it rapidly covers the soil. And the question here, if we would combine those two, would the celery be able to protect the leek against the negative influence of the weeds? That was the idea behind this. Now, if we look at light interception, which was measured in those systems, you can see that the intercrop, as expected, indeed is in between the light interception from celery and the light interception from leek. Leek developed very slowly, and even in the end did not result in full canopy closure. Celery develop way faster. And what we see for the intercrop here is that the light interception is much more close to that of the celery than it is to that of the leek. And that is something to keep in mind, because I will come back to that. This was another part of the experiment. So the crops were well established, and then seedlings from Senecio vulgaris were introduced. And they were introduced at 4, 6, and 8 weeks after transplanting of those crops. And then the number of seedlings that survived was counted. Now, initially, if they were introduced at 4 weeks after planting, for each of the crops, still many of the weeds survived. But then you can see that with a rapidly closing canopy of celery, if you introduce those seedlings at 6 or at 8 weeks, there is really a big mortality of those weed seedlings. That's opposite what you find with leek, because there the canopy stays open for a much longer period of time, and even at 6 weeks after the crop has been transplanted, still a lot of weed seedlings survive. Only in the end it gets a bit lower. Then if we look in the intercrop again, we can see that the number of seedlings that die is way higher compared to the leek monoculture. So in that sense, celery really helps to protect the leek against the weeds. This is more or less the idea, the principle behind it. In agriculture, and particularly in vegetable cropping, we make use of a weed-free period. That means initially we control the weeds, but then after a certain moment of time, the crop will be able to take over, because now the canopy is so well developed that you don't have to worry about them anymore. And you can imagine that the length of this weed-free period depends on how fast the canopy of the crop is able to develop. With leek, it takes quite a bit of time, and even in the end, still weeds might emerge and be able to develop and produce seeds that might give negative implications for the upcoming growing season. You cannot go in there with a mechanical weeding device, because that will damage the leek too much. So then you have to do manual weeding. If you introduce a intercrop of leek and celery, you can see that the weed-free period is much shortened, and after that period, the canopy takes over. So in this case, by introducing the intercrop, you have two major advantages. You have a reduced weeding effort, and you also have a reduced yield loss. Okay, if we look at other intercrops, and if we look at the literature that is available on intercrops and weed suppression, we looked, or there is a well-known publication from Liebman and Dijk from 1993, where they looked at both spatial and temporal crop diversification. So they looked at intercrops and crop rotations. And for the intercrops, they counted how the weed biomass in intercrop compared to the weed biomass in pure stands of the two component crops. And he found that in 8% of the situations, the weed biomass in intercrop was more than in both pure stands. In 42%, it was somewhere in between. And in 50% of the cases, it was even lower than the weed biomass in both component crops, in pure stands of those component crops. Now, we had a PhD student, Junfeng Gu, and she redid a kind of analysis. She came up with over 300 records, and she more or less observed the same findings. Also with her, in more or less half of the situations, the weed biomass was lower than in both pure stands, and only in few cases the weed biomass in intercrop was higher than in the pure stands of both crops. So mostly positive effects, and that illustrates that intercropping might indeed be a very good way for improved weed management. So then Junfeng dived into this a bit further, and we compared in first instance the weed biomass that was found in the intercrop with the wheat biomass that was found in the least suppressive crop. And then, of course, you would expect that this ratio is below 1. This ratio is put on a logarithmic scale, so if it's below 0, it means the ratio is below 1. And you can see indeed that on average, this ratio is 0.42, meaning that the wheat biomass in intercrop is 58% lower than in the weakly competitive crop. So really a big difference. If we did the same with the stronger competitive crop in pure stand, and we again went for the same ratio, then we noticed that the stronger competitive crop is doing a better job, but the difference is very minor. It's a ratio of 1.08, meaning that the wheat biomass in intercrop is just 8% higher than the strongly competitive crop. So the intercrop performs comparable to what the stronger wheat suppressor is doing. So wheat biomass in intercrop much closer to that of the stronger competitive crop. And here we look at the same data again, and we put the wheat biomass of the weaker suppressive crop at 100%. This is the wheat biomass in the stronger competitive species. The green bar represents what was observed in the intercrop. And here all data were put together. This is the average of this one, and you can see that the wheat biomass that is actually observed is way lower than the average of the two pure stands. So there's really a benefit for the intercrop. We then also separated the intercrops that were laid out in replacement design, meaning that the total density in intercrop was the same as the density in the pure stands. And we looked at additive intercrops where the plant density is increased. And then you can observe that in the additive intercrops, the wheat biomass that is actually observed is even lower than in the pure stand of the more competitive species. But of course, that's not just because of an increased plant diversity, it's also because of an increased plant density. And of course, we are aware that the same trick will work if we would increase the density of the pure stand. And so it's not a fair comparison. I think that is what we have to realize. We can increase, of course, the competitiveness by increasing plant density, but that's not only a result of an increased crop diversity. Okay, which mechanisms is responsible for this very positive effect? That is what we would like to know. And if we look at the performance of an increased species diversity for ecosystem services, then usually a distinction is made in two main classes of mechanisms. And that's not something that I have thought of. That is something you can find in literature. And so Laureau and Hector, a very well-known publication, they made this separation. And later on, Brooker also came up with this classification. The first effects are complementarity effects, and that could be either facilitation so that one plant helps the other, or it could be niche differentiation. And that, of course, will lead into an increased total resource use by the intercrop. And as a consequence, fewer resources are left for the weeds. And you can imagine that that will result in a positive effect. The second mechanism is what we refer to as a selection effect, and that is defined as a species which has particular traits, causing it to dominate that trait of the mixed plant community. And if we then think about weeds, we can imagine that a relatively well weed suppressing crop dominates the less competitive crop, and as a consequence, the total weed suppression of that mixture is higher than what you would expect. Two effects that could be responsible, or a combination of those two, that could be responsible for the improved weed suppression. The question now, of course, is, does it matter? If an intercrop provides good weed suppression, okay, great, who cares? Well, actually it's quite important to know which of those mechanisms is responsible. And that's for good reasons, because you want to find out what are good combinations of crops. And if the mechanism is a complementarity effect, then you have to look for species with partly different niches. And that might be difficult to find, to tell beforehand. So if you really want to look for that, it makes the screening complicated, because you have to do the field testing of mixtures. And if you have just a number of pure stands and a number of weakly competitive, a number of strongly competitive crops or varieties within a crop, you rapidly end up with an enormous amount of combinations you have to look for. The advantage is, if complementarity is really the mechanism, then it's very likely that that complementarity will also result in an increased yield, a higher land equivalent ratio. I guess that has already been mentioned yesterday, or
Hardly.
hardly. Okay, but it refers to an increased yielding ability of the intercrop. If selection effect is the main mechanism, then you have to look for species which differ in weed suppressive ability. You have to combine a stronger weed competitor with a weaker weed competitor. But that selection, of course, can already be done on pure stand level. So that means the field screening is way simpler. The disadvantage is, if that selection effect is the main mechanism, it might result in an overdominance of the stronger suppressor, meaning that the stronger suppressor not only outcompetes the weed, but also the weaker weed suppressor. And that is, of course, is not what you want, particularly if the less competitive crop is the one where you really are growing the crop for. So it is important to know which mechanism is responsible. And how can we identify which mechanism is at stake, is operative? Well, for that, we took as a starting point the law of constant final yield. And the law of constant final yield shows that if you increase crop plant density, the yield will go up. But in the end, you reach a point that plant density not really matters anymore, but it's mainly the amount of resources that is available that determines this final yield level. You can also see that initially increasing the number of plants results in a linear increase in yield, but once those crop plants start to compete among each other, then gradually it still goes up, but not at the same pace as at low plant densities. This is what is known as the law of constant final yield. And this is the rectangular hyperbola that describes this function, which characterized by two parameters and the number of crop plants. In fact, the yield of a crop, of course, is the number of crop plants multiplied by the individual crop plant weight, which is indicated with the W. And from here you can see that W is characterized as 1 divided by those parameters. Now you can see what's going on. When you increase crop plant density, you will have more plants, but at the same time, the weight of those plants, because this is in the denominator, will go down. And that, of course, is also what you expect. If you have many plants, they compete among each other, and they stay smaller. Still, the overall result is still an increase. So if you look at individual plant dry weight and you make a graph up against crop plant density, you see initially a very rapid decrease in individual plant dry weight, but in the end, when you move from 100 plants to 101 plants, it's not really that important anymore. You can also depict it in another way by taking the inverse of W, and then you see that a straight line shows up. And that looks like this. So here you have crop plant density. This is the 1 over W. That means the intercept here is BC0, and the slope of this curve is BCC. So if a crop is highly competitive among itself, the parameter BCC will be way larger, and this line will go up much more steep. And that means plants stay smaller when you grow them at higher density. Now, based on this, Kees Pieters introduced a new equation. And he said, in fact, what we observe here is an additivity of competitive influences. If you add the next crop plant, 1 over W will increase with a value of BCC. Now, if that is the effect of intra-specific competition, it's very likely that if you add another species, that will also result in an increase in 1 over W. Only, of course, this competition index might be different. That will be plant specific. But again, it represents the additivity of competitive influences. And you can do the same trick for wheat biomass, of course. This is, here it represents a crop, but you can also do the same for a wheat plant. So if a wheat is grown in isolation, it gets to its maximum size, which is then the inverse of BW0. If you now have a wheat population, then those plants, the wheat plants, will compete among each other. The intra-specific competition is referred to as the influence of the wheat on the wheat, so intra-specific competition, and this value will be lower. If you now find the same wheat population present in the crop, then it not only receives competition from the wheat, but also competition from the crop, characterized by the number of crop plants, the crop plant density, and this competitive effect of the crop on the wheat. And that is how we can quantify the competitive influence of a crop on the wheat. Again, important to realize that it assumes that competitive influences are simply additive. Now, if we think about the situation of an intercrop, we can first have a look at the pure stance of those two crop species. And for that, we can put together these equations. This refers to the wheat. This is the competitive influence of crop species number 1. The same equation, but here the competitive effect of the second species is included. If we now move to an intercrop, we can construct this equation, where here we find the competitive effect of species 1, and here the competitive effect of species 2. And there's a row included here because usually the crop plant density in intercrop is lower than in the pure stand. So we have to correct for that. Now it would be, if we want to understand what's going on in the intercrop, it would be very interesting to determine the values of those parameters. But if you want to determine those, you really need the two crops combined in different ratios at different total plant density. Usually that's not what is present. So that's not a way we can go. Does it mean that this is a dead end? No, not really. Because what we can try, we can see whether we can find an expression where the wheat biomass in intercrop is described as a function of the wheat biomass that is found in those pure stands. And if you do that, if you do the mathematical derivation, what you can show is that the wheat biomass in intercrop is identical to what we know as the harmonic mean. So it's not just the average that you find in intercrop, it's the harmonic mean. And how does the harmonic mean operate? Well, if you have a wheat biomass, if you find a wheat biomass in the first crop, the more suppressive crop of 4 grams per meter square, in the second crop, you find a value of 40 grams per meter square, then the normal average, the arithmetic mean, would be 22 grams per meter square. If you now use the harmonic mean to calculate the mean, then the ratio in the two crops is 50%, so that's 0.5 and 0.5. 1 divided by the wheat biomass in the first crop 1 divided by the wheat biomass in the second crop leads to this. And you can see that the wheat biomass that is expected in the intercrop is way lower than the average. So here we already have a very positive effect of combining two species simply because of additivity of competitive influences. And this additivity of competitive influences, in fact, represents the selection effect. It simply means that the more suppressive wheat species in intercrop will take a more than proportional share in suppression of the weeds. And the weaker competitive species is to some extent a bit suppressed by the more wheat suppressive species, and therefore it will contribute less than expected. But the overall result is a big advantage in terms of wheat suppression. So in conclusion, the wheat biomass in intercrop is estimated based on the wheat biomass in the two pure stands. The additivity of competitive influences represents, in fact, the selection effect, stronger influence of the more suppressive wheat species, crop species, and mathematically, this corresponds to the harmonic mean. So just to illustrate this a bit, if we have 3 different crops, crop 1 poorly wheat suppressive and crop 3 the most wheat suppressive, and the ratio between the amount of wheat biomass that develops in those crops is indicated here in orange, and the ratio is 6 to 4 to 1. If we now combine those 2 crop species in a field, but we put them on separate parts of the field, so there is no interaction between those 2 crops, it's simply half with crop 1 and the other half with the other crop, then you can see what develops here is simply the average of the 2 crop species in terms of wheat biomass. And if we look at it in more detail for the combination of crop 2 and crop 3, where the ratio between wheat biomass in pure stand was 4 times 1, and this is 4 times as high as for this species, and you now gradually increase the fraction of the more competitive species, then you will find a wheat biomass that is making a linear relation with those 2 pure stands. It's simply the average that pops up. If we then introduce the same 2 species in the same densities in a crop, but we now put it out as an intercrop, so the 2 species are intimately mixed, then the more wheat suppressive species will take up a larger share. And the additional share it will take depends on the difference in wheat suppressive ability between those 2 species. And what you gain from that is indicated here by the rectangle that evolves. And what you can see that if the 2 crops differ a lot in wheat suppressive ability, you have a major advantage. If the 2 crops do not differ so much in wheat suppressive ability, there is an advantage, but the advantage is way smaller. Again, if you plot it as depending on the fraction of the more wheat suppressive species in the intercrop, you can see that it does not develop in a straight line. It now develops in this bended curve. And the difference between the 2 is the additional wheat suppression you receive because you grow the crops as an intercrop. So that is what we refer to as the selection effect. And this line, in fact, represents the harmonic mean. And this is how it could look like in the field. Here we have a pure stand of rye. The soil cover is 85%, so a rapidly covering a crop, quite wheat suppressive. Here we have a pure stand of field pea. Soil cover is 35%. If we then look at the intercrop situation, you might expect half of this soil cover, 42.5%, half of this soil cover, resulting in a soil cover of 60%. But actually what you find in this situation is the rye covers about 63%, so more than you would expect based on the monoculture, whereas the field P just occupies 8%, which is less than you would expect from the pure stand of the field P. But if you look at the total soil cover is more than the simple average. So also this illustrates the selection effect. What will go on if, in addition to the selection effect, also complementarity will play a role? Well, then you would expect that there is an even further reduction in wheat biomass. And you can depict that in this way. Now, how can we distinguish between a situation where just the selection effect is operative or a situation where both the selection effect and the complementarity effect provide an improved weed suppression in intercrop? And this is the procedure we followed. We used the collected data set, and there we calculated the expected wheat biomass in intercrop based on the wheat biomass that was observed in the two pure stands using the harmonic mean. And then we compared this prediction, this harmonic mean value, with what was actually observed in the field. Well, if there is a close correspondence between those two, the conclusion will be, okay, intercrops do provide a better job, and it's because of the selection effect. If the wheat biomass is systematically overestimated by the harmonic mean, we conclude, hey, there is an additional mechanism at work. And then we would conclude that, hey, next to selection, there's also complementarity. And that is actually what we did. And this is what we observed. And of course, there is scatter. But if you look at what's going on here, there's quite a very good match between what is observed in the field and what is predicted with the help of the harmonic mean. And based on this observation, we conclude, hey, if we go for an intercrop, you might expect an increased weed suppression, and it is simply because of selection. Now, if you look at literature, many people will claim that the improved weed suppression in intercrop is due to complementarity. And of course, the reasoning is also making sense. The reason that complementarity does not seem to play a big role is probably because for weeds, it's very important what happens in the early stages of the growing season. If you're then able to quickly cover the soil, weeds will not stand a chance. Complementarity will be much more visible at the end of the season, and when the two crops are competing for the resources available in the soil. And then that might give an advantage to the intercrop. But weed suppression does not really profit from that, simply because in the early stages, the decision is already made. And the competitive relations are already being settled. Okay, now if we know that the selection effect is operative, what implications does that have for intercrop design? How we can design an intercrop in such a way that we can make use of this advantage? And this is what we derived. If you have, and for that we used parameter A, which represents the wheat biomass in the least competitive crop over the wheat biomass in the more strongly competitive crop. And over here, you can see the example where the wheat biomass in the more competitive crop is twice as low as in the weaker competitive crop. So there is an A value of 2. And you can see that the dotted line is what you would expect. The solid line is the prediction according to the harmonic mean. So there is an advantage, but there is not really a big advantage. If you look at a situation where the two crops really differ in competitiveness, then this is what you would expect, but this is what you actually find. So it clearly shows that the more the two crops differ in weed suppressive ability, the stronger the reduction in wheat biomass is. And this is the reduction in wheat biomass relative to the wheat biomass found in the weaker suppressive species. So here we can see that if crops differ in wheat suppressive ability, the advantage in terms of weed suppression will become larger, and a larger part of this advantage is due to the selection effect. Now, we also investigated that in the field. David Kotlenberg, who is conducting a PhD study on this topic, was almost completed. In 2022, conducted an experiment where he introduced 4 cereal crops, 3 leguminous crops, and in addition laid out all cereal legume combinations. And then he observed light interception, canopy cover, the weed biomass that developed, and also the crop yield. And this is the result for canopy cover, just as an example. And we find the same pattern which we already observed with the leek celery situation. This is the best weed suppressor because the canopy closes relatively fast. Triticale, this is faba bean, a much slower development. And in the end, it just reached more or less 100% of soil cover. The intercrop again is in between those two, but the canopy cover is much closer to that of triticale than it is to faba bean. So again, it illustrates the selection effect. Then he also collected wheat biomass. Now in this case, the red bars represent the wheat biomass in the cereals, in rye, in barley, and in triticale. So clearly, the low amounts of wheat biomass. The cereal wheat was an exception because it had a relatively high wheat biomass. The blue ones are the pure stands of the legumes. Those two, more or less, the lupin and pea, more or less had the same wheat suppression as the wheat. And here, faba beans showed to be the weakest wheat suppressor because there most wheat biomass developed. Then the green ones, they are the intercrops. And what you can see is that the intercrops are very similar to that of the cereal component in that intercrop. So here they are doing relatively well. Those two intercrops are not doing that well because wheat, the weaker of the cereal, the weaker suppressor of the cereal crops, was not doing a very good job. So that means it also did not really result in an advantage compared to the pure stands. So if we now calculate the harmonic mean based on the wheat biomass of the two pure stands, and we compare that with what was observed in the field, then for barley, but also for rye, for wheat, and for triticale, we found a very good correspondence. So it really shows that the harmonic mean is a good way of predicting what you can expect in the intercrop. If we compare it with the arithmetic mean, then for the more wheat suppressive cereal species, we find a clear difference between the arithmetic mean and the harmonic mean. So showing that growing the two crops in an intercrop really has an advantage. Same here for rye, same here for triticale, except for the intercrops with wheat, which was not competing with the wheats that well. And as a result, the arithmetic and the harmonic mean do not really give an advantage, do not really show a difference. So there is not really an advantage in terms of wheat suppression if you combine wheat, in this case, with the legumes. So it really shows that if you want to have an advantage in an intercrop, you really need species that differ in wheat suppressive ability. Of course, there's also a downside to it, because if you have crops that really differ a lot in wheat suppressive ability, the more suppressive crop might also negatively affect the weaker competitive crop. And that is what you can see here with the data from rye and two leguminous species. This is the land equivalent ratio for the system as a whole. But here you can see that rye represents or got a yield that is more or less similar to what it obtained in pure stand. But for the legume, the wheat, the yield is way lower. And so if they differ too much in wheat suppressiveness, it also has implications for the yield of the crop. If we look at the situations where wheat was used as the cereal, and the wheat was not that competitive, and the difference between the wheat and legumes was not that high, you can see the land equivalent ratio is just a little about 1, and the two components are more or less equally represented. So wheat does not outcompete the legume because they are equally wheat suppressive. So what it clearly shows is that you have a trade-off between wheat suppressive and yielding ability. If the crops differ, there is an advantage in terms of wheat suppression, but there is also the disadvantage that the stronger suppressive crop outcompetes the weaker one. Okay, then we looked at another factor. If we talk about design, that's the mixing ratio. And then we find a very interesting difference. Here again, the situation where the wheat biomass in the two pure stands differ twofold. You can see that the largest difference between the arithmetic and the harmonic mean, so actually the selection effect, is found very close to a ratio of 50%. However, if the two crop species differ really a lot in wheat suppressiveness, in this case the ratio is 8, so the wheat biomass in this pure stand is 8 times as high as in this one, then you can see that the largest advantage in terms of the selection effect is found at a much lower contribution of the stronger competitive species. And that, of course, gives us a nice tool for manipulating the intercrop. If we now lay out the intercrop with a smaller contribution of the more suppressive species, it already has huge implications for wheat suppression, and probably the weaker suppressive crop will not be outcompeted that much. Now that was also validated in the field, again by David in 2023. And here he conducted an experiment where he just included triticale and faba bean. He laid them out in different mixing ratios, 3 rows of triticale and 1 row of faba bean, 1 row of triticale versus 1 row of faba bean, or the other way around, 1 row of triticale with 3 rows of faba bean. Now this is the wheat biomass that developed in legume at 2 different densities. This is the wheat biomass, which was way lower, that developed in the triticale. And when you look at the intercrops, you can see that even the intercrop where just 1 row of triticale was introduced next to 3 rows of faba bean, you still have a very good wheat suppression. So this gives us good options for designing a system that is really good in terms of yielding ability, but also still good in terms of wheat suppressive ability. Then the final one, spatial arrangement. Strip cropping systems have been mentioned already a number of times. Of course, in the strip cropping system, you'll have a less intimate mixing between the different crop species. It's only at the edge. So what does that mean? If we have a weakly suppressive crop and the wheat biomass is like this, if we have a stronger suppressive crop and the wheat biomass is way lower, I think 8 times lower, then the arithmetic mean is found exactly in between. The harmonic mean shows that in this case, the wheat biomass in intercrop is way lower than what you would expect, again, due to the selection effect. The question now is, and this represents a situation where the intercrop is severely mixed, what happens if you use strips of more than 1 row? So if you, in fact, reduce the intimacy of the 2 crop species. So here the number of rows within a strip is indicated. And then you can see what we can expect. If the strips contain too many rows, they move towards a monoculture, and the wheat biomass you find in the entire system gets closer to the arithmetic mean. And actually what this tells us is that with every doubling of the number of rows in a strip, only half of the advantage remains. So if you are working with 2 rows within a strip, only 50% of the advantage remains. If you then move to 4 rows within the strip, it's just 25%. And if you then move to 8 rows within the strip, the advantage is only 12.5%. So the intimacy for having this advantage is really very important. Now, of course, this was also tested in the field, and it was done by Xiaoyi, who's here around here. What she did is she also worked with triticale faba bean, and she then varied the strip width from 1 row per strip to 2 rows, 3 rows, 4 rows, 6 rows. This is the weed biomass in triticale, so very low again because it's a weed suppressive species. This is the weed biomass in faba bean. Then if you have a good mixture, you'll find more or less here the arithmetic mean of those two weed biomasses. But then if you increase the number of rows within a strip, gradually the system moves towards the arithmetic mean. And here it goes a bit faster than what we expected, but the pattern is more or less comparable. Okay, so to summarize, selection is the most prominent mechanism responsible for the above average weed suppression of intercrops. So intercrops are really doing a good job, but it's not because of complementarity. If it comes to weed suppression, it's mainly because of selection. Conditions for a positive weed suppressive effect are a difference in weed suppressive ability between the two species. If they are equally weed suppressive, you don't find a benefit. And you also need close proximity of those two component species. Intercrops in additive design, so if you increase plant density, is in fact the only means for increasing the weed suppressiveness of an intercrop if there is no difference between the weed suppressiveness of the two component species. We also observe that even in relatively smart fractions of the more weed suppressive species already gives a considerable increase in weed suppression. And selection is particularly suited for protection of a weakly suppressive crop, but care should be taken not to overprotect, because then it will simply be at the cost of the weaker crop, the weaker weed suppressor. And that's about it.